Okay, so yeah, I was saying that our TSF residual might have some impacts on the cosmology, which we can quantify with those statistics. But we can also look at their impacts directly on the galaxy shapes, and that's what we call the PSF leakage, where basically we try to measure the residual ellipticity that might be left in the galaxies. So here we're measuring it for both pipeline, shape pipe, and lens fit, and we managed to reduce this leakage to less than 1%. So yeah, for lens fit, we have some things going on for the largest value of the ellipticity, which we are currently investigating, but it doesn't seem to show very badly in other tests that we are making. So another way to look at this leakage is actually to see if there is a scale dependence. So that's what is shown in the plot on the left here for both pipeline, where we see that the leakage is between 2 and 3% for all scales. So for shape pipe, this seems to have a slightly more dependence at higher scales, which we are also looking into, and we hope that by improving our PSF model, we will reduce the systematics, and we can directly link also this leakage to the cosmology that we want to do. And this is the plot on the right, where here the dashed line represents a 5% contribution of the systematic signal into the scientific signal that we are interested in. So of course, it's a quantity that we want to minimize. And we see that there is already a lot of scales which are already usable for science, while the largest one might have some systematics that we should take care of. Okay, so now we have cross-validated the PSF and also the PSF with the galaxy. So now we can look at the galaxy themselves. And here we are using a property that the lensing signal by itself should not create any B modes. So we can actually use that as a null test and make sure that we verify that with our data. So here, for example, we do it with what we call the COSEBIs. And what we are interested in this plot are the orange lines. And we see that for both pipeline, they're fairly consistent with 0, meaning that we are not measuring B modes, or at least no systematic that creates B modes. So another way to look at this is by looking at what we call the pseudo-CL. So here there is a scale dependence as well. And we see that for most of the scales, both pipeline are pretty good. So shape pipes tend to have some B modes on large L, meaning small spatial scales. So it's also something that we are investigating. But those first results are very, very promising and also kind of in agreement with what other pipelines are doing. So right now we have processed around 3,600 square degree. So it corresponds to the CFIS DR3, which we have divided in 7 patches. And we've made our first internal release of both catalogs. So they have a slightly different area because not using the same masking, and also Lensfit use this reprocessing with tele, which also have an impact on their footprints. But both catalogs have around 100 million galaxies, also slightly different statistics, but given that the processing are not exactly the same. But those catalogs are already available for all the unions people on Canfar, and there is some explanation on how to use those catalogs and a little bit more explanation on the statistics. So before the conclusion, I wanted to say a few words also on the redshift estimation. So as Jean-Charles presented, unions is multi-band, but we don't have all the bands already on the full area. So what we are doing is just trying to get the redshift distribution for the entire sample. And for that, we use a method that is called the self-organizing map, where basically we use some information that we have from CFIS lens for the photometry and also some spectroscopic survey to try to, in some ways, reweight the redshift distribution, the true one from the spectroscopic sample, to match the one we have with the unions galaxies. And it works pretty well. We managed to get the mean delta Z less than 0.01, which is very good with method like that. And here you have an example of the N of Z that have been derived for both pipelines. So as you can see, there is no graduation for the Z-axis because we are blind to the redshift distribution in order to not plate our cosmological analysis. So this N of Z is also public for all the unions member. And you have an unblind version and also 3 blinded version of this N of Z, which can be required depending on the kind of analysis that we want to make. So in conclusion, we have our first release that is done. We have an accurate N of Z that goes with it. Hopefully, pretty soon we're going to have multiband and photo-Z. So there is some work in progress already to try to get the photometric redshift for this 800 square degree, which is also increasing through time. So already getting some very interesting results on this. And we hope that soon we're going to move from this approximate N of Z to a realistic redshift distribution. We also have some work on image simulation that is incoming also in multiband to try to test our pipeline very deeply, and also the photometric redshift estimation, the simulation are going to be very, very useful. There is a first analysis that have been done with ShapePipe and published and available on arXiv if you want to have a look and see in more details how a pipeline like this works. And there is some preliminary science which are going to be presented by Mike just after me. And yeah, thank you.
Any questions? No, Maribeth in the audience? So just one for the shape measurements. How deep are you going? So do you define a signal to noise limits in R-band to accept?
So, well, actually, both pipelines behave very differently. So for lens fit, it's a bit complicated to do that because they have a sort of Bayesian estimation. So you cannot make straight cuts like you would do usually with more classical approach. So it's more based on the weighting that you have for each of the ellipticities. So at the end, we end up with more or less the same magnitude distribution for both samples. For ShapePipe, we made a straight cut at SNR 10, just because below that, the signal is not very useful. So the sample that we use for lensing, I think, reach magnitudes 23.5 in the R-band. But we hope that by tweaking a few things here or there to go deeper than that.
And the peak of your N of Z is around 0.5 or?
No, it's deeper than that. It's between 0.65 and 0.7, something like that.
So that's,
but yeah, I don't know the truth. So.
Any question?
I was just wondering, do you expect it to be a problem once the mirror gets repaired and the actuator is changed? I suppose the PSF will be very different.
Yeah. So yeah, I was really worried when I see this plots. So yeah, I will continue to do the systematics that I was computing, and I think I will focus only on the data that come after this have been fixed to see if there's any impact. But the thing is, since we are doing the correction independently, if the correction is if the problem is fixed appropriately and we manage to get the same sort of residuals in our PSF elasticity, even if the PSF changed, if we manage to have the same error at the end, it doesn't really matter if the PSF is different. So yeah, we just hope that it can be fixed and that our model will be able to capture the new one.
Okay, so let's thank Axel.